Okay, and so we're talking about empirical and molecular formulas. So I already defined them for you. So you know that an empirical is simplest whole number ratio, and that a molecular formula is just the number of atoms needed to make that molecule, but the molecular is just a multiple of the empirical. And so we actually can determine these from data given to us. The way that we can do it is starting with one way, is you guys are going to convert from mass to moles. Remembering I put this option A in here because to get from mass to moles, you use the molar mass. So you'll take your mass, divide it by your molar mass, it'll give you your number of moles. Then the next step is dividing all of the resulting. So what you guys get for your answers, mole numbers, by the smallest mole value. And then your last step is just to write the formula. And typically how we write this formula, and this will go for you guys, whatever way I present the elements. So if I say C, then H, then O, that is the same way you'll write your formula, CHO with a subscript. So typically just write it however it's presented. So let's start with an example. So we want to find out what the empirical formula for a 55-gram sample of a compound that contains 0.9 grams of hydrogen, 12.2 grams of nitrogen, and 41.9 grams of oxygen. I forgot the little G there. Typo. And so the first step we're going to do is convert mass to moles. So we have to do this for each of our elements. And so first we're starting off with hydrogen. So you just take your 0.9 grams of hydrogen, set up your conversion factor. In this case, we're talking about elemental state of hydrogen. So you're not using 2 as your mass, okay? We're not talking about hydrogen gas, just one hydrogen. So you're using 1.0 grams per 1 mole. Nice little 1-to-1 ratio there. We have 0.9 moles of hydrogen. Do the same thing for nitrogen. We have 12.2 grams of N. Using the molar mass of 14.0 grams per mole, that gives us 0.871 moles of nitrogen. Then for oxygen, 41.9 grams of O. We have a molar mass of 16.0 grams per mole. That gives us 2.62 moles of oxygen. Does everyone make sense what we're doing? Just one of the earlier conversions we've learned in this unit. Okay. Now, the next step, all you have to do, divide all the resulting mole numbers by the smallest value, and then we're rounding to a whole number. This part B, this is figuring out the subscripts for each element. So what was the smallest mole value in part A? Yep, 0.871 moles for nitrogen. So this is going to be our denominator for the 3 elements. So starting with hydrogen, if we have 0.9 mole hydrogen, we divide that by 0.871 moles. And rounding to the nearest whole number, it's about 1 mole of hydrogen. Now we do nitrogen, which because nitrogen was the smallest, I'm still going to show the work, but that's also going to come out to be 1 mole of nitrogen. And then lastly, oxygen, 2.62 moles of oxygen divided by 0.871 moles. This is going to give us about 3 moles of oxygen. Any questions on this process? Just recapping that we got the 0.871 because it's the smallest of the 3 resulting moles here. Okay, so now all you have to do is just write our formula. So we're writing it how it was presented. H, then N, and then O3. So the 3 from the 3 moles is now our subscript. Any questions? Cool. I'll take that as you guys get this. Okay, option number 2. Let's say instead of being given masses, you just have percents. The first thing you want to do is you're just going to assume that you have 100 grams of a compound. Now, you could assume any amount of grams, but with percents, it makes sense just to assume 100 because it's just going to translate into their mass. So once we assume 100 grams, we're going to have masses, and we're going to, again, convert those mass to moles. And we're going to divide all resulting mole numbers by the smallest mole value. So pretty much the only extra step here is you just have to come up with the masses to begin with. So in this example, it's just saying that the percent composition is 20% magnesium, 26.7% sulfur, and 53.3% oxygen. What is the empirical formula? Step 1, assume you have 100 grams of a compound. So then you're just taking what is 20% of 100 grams, 20 grams. Then if we have 26.7% of 100, that's 26.7 grams of sulfur. Does it start to make sense why we assume a nice even number of 100? Makes it pretty easy. Like I said, if you use something other than 100, that's fine. Just makes it a little harder on yourself. So now we have our starting masses, and now we just have to convert from mass to moles. So sorry, you're gonna have to go on to the next page for this guy. All right, so we're starting with first magnesium. If we have 20 grams of magnesium, the same process of using molar mass, magnesium weighs 24.3 grams per mole, giving us 0.833 moles of magnesium. Then we have 26.7 grams of sulfur, which weighs 32.1 grams per mole, giving us 0.831 moles. And lastly, oxygen, 53.3 grams, converting with its molar mass of 16 grams per 1 mole. That's going to give us 3.33 moles of oxygen. So now that we have found all of our molar values, which element has the smallest value? Sulfur. So that 0.831, that's our smallest mole value. So we're going to divide, again, each one of the mole values by 0.831. So 0.833 moles of magnesium, all divided by 0.831 moles. We have 1 mole of magnesium. Then we know that we're going to have 1 mole of sulfur, as that was our smallest mole value, but I'm just showing the work anyway. And then oxygen, 3.33 moles of oxygen divided by 0.831 moles. Gives us 4 moles of oxygen. So again, we're rounding to a whole number. This may not be exactly 4. It rounds to practically 4. I was going to show you an example. So now for writing the formula, magnesium, sulfur, oxygen, 4. All right, any questions on this? Okay, so how do we find the molecular formula? Well, like I said earlier, the molecular mass is just a multiple of the empirical. So there's a good example here with CH2. If we know that CH2 has a formula mass of 14, if we're multiplying these number of atoms and elements, you're doing the same thing to their mass. So CH2 times 2, you get C2H4, and its mass is equal to 2 times 14. So it's very simple here. And so we may be given problems that we need to determine what multiple to use. And so all you're taking is the molecular mass of the one in question, the mass of, you don't know what the molecular formula is. You divide it by the empirical formula mass, and then you get your multiplier. So the example here is if we have a molecular mass of a compound that has an empirical formula CH2 is 42.1 grams, what's its molecular formula? Well, first, you need to figure out the molar mass of the empirical formula. Well, this was already calculated for us. We know it's 14, but just to remember, you have 1 mole of carbon plus 2 moles of hydrogen, you get 14. So all you have to do now is take the mass of your compound, 42.1, divide that by the empirical formula mass. You find out your multiplier is 3. So now all you have to do to get your molecular formula is you're taking 3 times CH2, which leaves you with C3H6, and that is your final answer. So once you find your multiplier, you're just incorporating that to the number of atoms. Any questions on finding molecular formula? Okay, the only last thing I want to note is that if you're working with gases, density is also proportional to the molecular mass. So the denser the gas, the greater the molecular mass. So if I'm telling you that there's 2 unknown gases, one has a density of 5 grams per mil, one has a density of 10 grams per mil. One of them is CH4 and one of them is C2H8. C2H8 will have the more dense value. So any questions on today's material? Okay, so what we're doing today is I have problem set 4 ready for you. So